Popular science writer and former professor, Saha Institute of Nuclear Physics, Kolkata. He is a theoretical physicist and emeritus professor in the physics department of Calcutta University, a writer, a linguist, a poet. His main areas of research is particle physics. Apart from the scientific contributions, he has authored well-known textbooks in physics as well as several popular science literature in Bengali to popularize science. He received his master's degree in physics from Calcutta University, PhD from Carnegie Mellon, Pittsburgh in the year of 1983. After that, he was associated with University of Maryland, University of Massachusetts, University of Oregon, University of Texas as postdoctoral fellow before he came back to India in 1994. In 2004, he received Rabindra Smriti Purishkar, and in 2011, Ramendra Sundar Smriti Purishkar. Professor Palash Baran Pal.
So the topic of my talk, the title of my talk is Scientific Temperament and Science Education. And because of the quite constrained time allotment, I have written it down, so I'll just read it from here, which probably will not be very exciting, but it will be conducing to the sleep, if you want. When one talks about scientific temperament, or rather the lack of it in our society, one often blames our science education for the state of affairs. For example, the web page announcement of this conference contains the following sentence: "Our education, particularly at the school level, does not teach the learners to think rationally and act logically," unquote. Assuming that it is true, it is further assumed that one should try to modify school education in order to accommodate rational and logical thinking. This is the premise that I will try to analyze in this lecture, and I will offer my thoughts on this premise. The first question: is the allegation against school education really true? Certainly, at school, a student has to learn a lot of things by committing them to memory, without any thought or analysis being spent for any of them. This set of things includes the alphabet, the words in a language, the numbers, and even simple arithmetical operations, the multiplication tables, almost all of knowledge of geography and history. Certainly, logical reasoning is not promoted by any of these, but one would hardly want to do away with them for that reason. However, it is also true that in the secondary school, everyone has to learn Euclidean geometry, considered a pinnacle of logical structure. Why then one complains about the absence of logical thinking in school curriculum? To put it more bluntly, if Euclidean geometry is not logic, then what is logic? My guess as an answer to that question is the following. We know that there are two kinds of logical systems, inductive and deductive. Euclidean geometry is a deductive logical system, and this is not the kind that one has in mind when one talks about scientific temperament. Rather, by that phrase, one thinks about the decisions made by a person when he or she tries to connect different phenomena. This type of logic, the type of logic used in such situations, is mostly inductive. Inductive logic is used in the sciences, not in mathematics. Of course, science is also taught at the school level. Why doesn't the teaching of science inculcate a scientific temperament in students? Or does it? We'll come back to this question later. Before that, let us ask the question whether our school curriculum is drastically different from that of other countries that we know about. And remember that I am restricting myself to school curriculum, not college or universities. In other words, to what extent is this a global problem, and to what extent is it a problem specific to our system? More or less, school education contains the same kind of things in every country: language, literature, mathematics, science, history, geography. To the best of my knowledge, there is no education system that tries to teach something called scientific temperament consciously or explicitly. It develops from the study of science, just like historical awareness develops from the study of history, although history books do not have a chapter with this title. Where the Indian school education system is vastly different from the systems in many other countries is the amount of material contained in the curriculum. By the time a student of science passes a higher secondary examination, he or she has to learn so much of physics and chemistry and mathematics that I often wondered, looking at the textbooks of my own children, what would they do with the rest of their lives? The story is not very different at the secondary school level as well. With the pressure of this huge syllabus, a student cannot afford any time to think independently about anything. The entire childhood and entire early adulthood is spent on gathering information rather than developing thoughts or analyzing information on any subject. And of course, without any thought, temperament cannot grow. So the first thing that should be done to our school curriculum is to reduce the load of the syllabus. It is not really necessary that a student graduating from a higher secondary school would know calculus or nuclear reactions or the properties of obscure chemical compounds. All these things and much more should be scrapped. I'm not saying that a course of calculus should be replaced by a course of scientific temperament. I really don't think everything can be learned at school. We do not teach kindness or sympathy in the curriculum. I have never heard a kindness course for my children. There are some kinds of things which ought to be learned from the society at large, not from the syllabus. And if a student looks at our society and sees things, some of the things that Ajit has already beautifully pointed out to you, and the feudal structure of the society, and also decision-making instances, like one sees big glass buildings being built in a hot country, where after building the glass building, you had to put air conditioner to keep oneself comfortable in that building. Trees are massacred for almost no reason. People setting their air conditioner to 18 degrees when it is a very pleasant 27 degrees outside and there is absolutely no reason for turning on the air conditioner at all. Water and air are being polluted every day without any serious effort of controlling the damage. In this kind of a situation, surely a student is not encouraged to think about the consequences of such acts. One might argue that I am putting the cart before the horse. That people do not think about these problems because our education system does not teach them to think scientifically about these issues. For people who would argue this way, I would present some thoughts regarding science education at school. First, the question of the medium of instruction. A huge proportion of students learn science and almost all other subjects of study in English. This is not the language that is spoken in the society in general. Thus, the problems of life seem disconnected with the problems of the curriculum. It is probably because of this reason that Indian science research is often not very imaginative. India produces excellent scientists who can make excellent follow-up work on a model proposed by someone else, but scarcely proposes a model himself or herself. Coming down from the research level to the daily life level, people can read arguments given by others, but hardly tries to develop one's own argument about anything. They can repeat the argument of others, but hardly tries to develop their own argument. It is easy to say that the solution is therefore to teach everyone in his or her mother tongue. The practical hurdles are huge in a country like India. Suppose a Bengali child starts going to school in Bengal, learning science and other subjects in Bengali. Then, when the child is 10 years old, the family has to move to Chennai. What will happen to the child's education if everything is going on in mother tongue? So there are practical problems, and the problem is not just ours. In the modern world, people feel the necessity of moving from one place to another much more often than, say, half a century ago. In my opinion, one has to face a situation where education in English or some such global language will be more and more popular. We therefore need other methods for connecting science with life. It has already happened, if not at the school level, but at the college or university levels. Nowadays, many colleges and many universities teach some courses, not everything, but some courses in English, and that's to attract foreign students. It has become more common after the European Union, where within Europe there is a lot of mobility of people. So we need to find other methods of connecting science with life. And this brings me to the second point. In my opinion, the science curriculum should be redesigned, where scientific issues will be discussed in the context of phenomena that one observes. So not starting from a law, but starting from the phenomena. For example, let us talk about physics. A student of class 5 should start physics by learning about energy, about different kinds of energy. He or she doesn't have to be very quantitative about how to calculate the kinetic energy, but will have to have the idea of energy. And at this point, the student should be able to relate to electricity, to the energy of a running automobile, for example, to the energy of a river flow. And the student should also learn that energy can be produced only at the cost of energy. In other words, should learn the idea of energy conservation. From this, one can jump onto some environmental issues about what energy is useful for us and what is not. Then one can learn about how simple machines work, and so on and so forth. In chemistry, one should start with the chemical properties of our food or about the chemicals that we use at home. For example, I was never taught why a soap removes oil or dirt from our skin. And I think a child should be taught that. Or why milk curdles when a lemon is squeezed into it. So one should start with questions like this, which would inculcate some amount of knowledge about the things happening around the student. I wish to give the similar kinds of examples about biology, but my knowledge of biology is so embarrassingly bad that I do not dare. There is another thing that I want to suggest. Along with the principles of science, one should teach some amount of history of science. Both these aspects, namely the principles and the history, can be carefully mixed up in popular science books. They can tell students not only about the theories or the discoveries, but also how the ideas were conceived, how the discoveries were made. They can give accounts of attempts that did not work, giving the student an idea of why they failed. That would teach a student how a scientist or a group of scientists zeroed in on a discovery, and it also shows the interconnection of ideas, and it also demystifies the scientist in the eyes of the general student. Let me give an example. of how this method might be effective. Any student learns Newton's law of gravitation at school. The law says that the force of gravitation between two objects is inversely proportional to the square of the distance between them. The textbooks never say how Newton arrived at this inverse square law. It says some apple falling, but apple doesn't fall with a 1 over r square written on it. So how is apple related to 1 over r square? What Newton needed, first of all, assuming that an apple fell, what he needed, first of all, was the bright idea that the moon is in fact also a falling body, not just the apple. Just like a fruit falling from the tree, the moon is also falling towards the earth. The only difference is that the moon has a lateral motion which does not allow it to reach the ground. So by the time it falls some distance, it also moves laterally so that it doesn't reach the ground. So that's why it goes around. Once he got this idea, he needed to know, let's just decide. From this idea, how does one reach 1 over r square? He needs to know the following things. Number one, the force that acts on the apple and the force that acts on the moon, or at least the ratio of the two, and the distances of the apple and the moon from the center of the earth, let's say. So the radius of the earth and the distance of the moon. So these are the things that Newton needed to know. How did he know the distance to the moon? How did he know the radius to the earth? He did not calculate any of these. These were determined by others before him, and he just used the results. How were they determined? Okay, I'm not giving the answer, I'm just raising the question, that it's interesting and important for a student to know the answer. And next, how did Newton know the forces at the two places? The acceleration due to gravity on the Earth's surface was measured by Galileo. With the rudimentary methods of measurement of time, how was it possible at that time? How could he measure an acceleration of such magnitude when there were really no clocks? Discussion of these questions will bring about another thing, which I was calling interconnections before. It will show that the law of gravitation could not have been arrived at without the laws of motion before that. Take this thing, for example. From the acceleration due to gravity, Newton related it to the force of gravity. That is the laws of motion. That is Newton's second law, which relates the acceleration to the force. And then also, the force on the moon was obtained from the moon's distance and the moon's angular speed. The moon's angular speed is easy to find. You know roughly how much time the moon takes to complete a rotation. But you have to know the distance. And then from that, you'll have to calculate the force. And that could not have been done without the concept of centripetal forces and their magnitudes. It's quite exciting to know the way Newton put all these pieces of the jigsaw puzzle together to arrive at his inverse square law. It is, of course, true that this method by itself cannot constitute the entire training of science. Some amount of science should be known in order to appreciate these stories. I'm suggesting that both kinds of resources, the traditional textbooks and the popular science books, can go hand in hand in the teaching of science. Or maybe the two kinds can be combined into one kind of book. That's a matter of semantics. We should not restrict this method to science alone. My dream really is some kind of course in the syllabus called Origins or Sources or something like that. In this course, a student will learn how the law of gravitation was arrived at, just what I just described. The student will also learn how the birth date of Jesus Christ was determined to be 4 BC, how the sources of the river Nile was found, how different calendars evolved in different civilizations, how we moved from the metal age to the plastic age, and many such things. This will make a student aware of the romances of not only science, but of history and geography and many other things, and in general, about the whole process of learning. Of course, everything cannot be taught in just a 1 semester or 1 year course in school, but then the student doesn't spend just 1 year in school. The student spends much more than a year, so there is a lot of time and there is a lot of things we can do. Done.